Today in class 12th, I am taking the topic, the explanation of paramagnetism. We know that the magnetic properties classify the material into the three categories. One is the diamagnetism, second the paramagnetic, and third the ferromagnetic. So today I am taking the explanation of paramagnetism. And this we know that the electron moving in the orbit gives the magnetic moment to the atom. So the atom behaves like the magnet, which is called the atomic magnet. The substances which are feebly attracted by applied magnetic field are called paramagnetic material. Paramagnetic substances. Suppose this is a plate on which we are having a paramagnetic material. This is the paramagnetic material. And this is in absence of magnetic field. Magnetic field. Now we are having this magnet. This is our north pole. This is our south pole, and this plate is placed. This plate is placed here like this. Then there is this shows that this material is collected at this near this south pole, north pole, and the south pole, having some depression between at the center. So this shows that this is being attracted by this north pole, and this is also being attracted by the south pole. So this shows that this material is feebly attracted by the applied magnetic field. Paramagnetic substance in presence of magnetic field. Now this paramagnetism is exhibited by those materials whose atom contains one electron in the outermost orbit. The single orbital electron provides magnetic moment as given below. M equal to N into MB, where N equal to 1, 2, 3, 4 and so on, the principal quantum number, and MB, Bohr magnetron. And its value is 9.27 into 10 raised to the power minus 24 joule per Tesla. It means the single electron provides so much magnetic moment. If suppose the electron is in the first orbit, then this will be now only 1 MB. If this is in the second orbit, then this 2 MB. This is in the third orbit, then this is now 3 MB. So, as the principal quantum number increases, the magnetic moment increases. The paramagnetism is found in those substances whose atom has one electron in their outermost orbit. So there is one electron that will provide the magnetic moment. The atom has its own magnetic moment. So it behaves like a magnet called atomic magnet. So atom already behaves like the magnet. It means that the single atom is not without the magnetic moment. In a sample of paramagnetic material, the atomic magnets are randomly arranged due to thermal energy. So magnetic moment of the sample is equal to 0. So magnetic moment of sample is 0. Since in a sample there are a number of atomic magnets and these magnets are randomly arranged in such a way that the net magnetic moment of the sample is equal to 0. So this is like this. This is the paramagnetic material or the sample. The atoms are like this. These are the atomic magnets. This is like this. They are randomly arranged. So the magnetic moment is equal to 0. Net magnetic moment. This is equal to 0. So this is when the magnetic field is not applied. In absence of magnetic field. And now suppose the magnetic field is applied. Then they become like this. This is the magnetic field applied in this direction. Then they are arranged. Some of them may be not in the direction of magnetic field. So this is the net magnetic moment, and this one is not 0. Net magnetic moment is not equal to 0. This is when we have applied the magnetic field. When magnetic field is applied on the paramagnetic material, magnetic sample, the atomic magnets get aligned in the direction of applied magnetic field. Magnetic field. Magnetic field due to the torque acting on them. So some of the atomic units do not get aligned. This is due to the thermal energy. This alignment of atomic magnets is opposed by thermal energy. So very few atomic magnets in direction of magnetic field. So this says that the net magnetic moment is not zero, but the maximum number of atomic magnets are aligned in the direction of the magnetic field. So the material is getting magnetized in the direction of magnetic field. Thus, paramagnetic material gets magnetized in the direction of magnetic field. Direction of magnetic field. So now we have as the magnetic field is switched off, the paramagnetic material loses its magnetism. So now we have the intensity of magnetization. This I equal to positive, because this is gaining the magnetism in the direction of magnetic field, so I will be positive. So susceptibility is positive. This is equal to positive. So we are having this in the way that is, suppose this is now I in this direction, this is the applied magnetic field in this direction, then this is now I is proportional to H. This is for, so this I is positive and I increases with the increase of this applied magnetic field. So I depends upon H, or the magnetic field B. Relative permeability. Now this mu r, this is equal to positive, or this mu r is greater than 1. So we have the relation mu r equal to 1 plus chi. Chi the susceptibility. So this mu r greater than 1, then chi is greater than 1. So this chi since this mu r is greater than 1, so chi equal to positive. Chi is equal to positive. Now you can have the magnetic permeability. Magnetic permeability of paramagnetic material. Paramagnetic material. Now this mu r equal to mu upon mu naught. Since mu r is greater than 1, mu r is greater than 1, so mu is greater than mu naught. The magnetic permeability of this paramagnetic material is more than the magnetic permeability of the free space. This susceptibility depends upon the temperature of the material. The susceptibility is inversely proportional to the absolute temperature, and this chi is inversely proportional to 1 upon T, and this chi equal to C upon T. This is not Curie law. Curie law. This C equal to Curie constant. And it has the unit of Kelvin. Unit of C. This is now K. Kelvin. So this satisfies the equation. This satisfies the paramagnetism that when the magnetic field is applied, then they get the magnetism in the direction of the magnetic field. So they are freely attracted by the magnetic field. And for these, the intensity of magnetization is positive, and this varies with the applied magnetic field. And so this I is proportional to H. So this is dependent upon H. And moreover, this the relative magnetic permeability is positive, and this is more than 1. So the susceptibility is positive for this one. And this susceptibility depends upon the temperature, that is inversely proportional to the temperature. So this chi varies with the temperature. So now I will show you the graph. This is now suppose chi. This is now your temperature T on this side, then it is like this. So this shows that this chi is proportional to 1 upon T. And if we are having this to be like this one, then this is now suppose I, and this is now your 1 upon T on this side. So this will be the straight line. This is now chi. This again shows that this chi is proportional to 1 upon T. This shows the variation of the susceptibility with the temperature. It means that when temperature is increased, susceptibility decreases. So the substance become more and more dimagnetic as the temperature is increased. So this paramagnetic material depends its magnetic property depends upon this temperature. And when the temperature is increased, susceptibility decreases. It means that the material become less and less feeble to acquire the magnetism, and that its magnetism losses as the temperature is increased. So this is about the paramagnetic material. Now I am telling you some examples of paramagnetic materials. Examples. Examples. There are so many examples of paramagnetic material. That is the sodium. This is now liquid oxygen. Oxygen, and this oxygen gas also. O2 gas, and then we have CuCl2, aluminium, and that lithium, magnesium. Lithium, magnesium, and other examples are cesium, tungsten, and uranium, platinum, etc. And now I show you the magnetic field lines. Suppose this is the paramagnetic material. This is paramagnetic material, and suppose these are the field lines. This is the magnetic field, applied magnetic field B. And what will happen to the inside of this one? This is suppose coming from this north pole. Then this will be the south pole. So magnetic lines of force are like this in this one. This is, now I can show you. Now then, like this. Now here and then in this side and then here so inside the paramagnetic material the field lines support the electromagnetic field and outside that this opposes. So this happens that inside the material the magnetism is in the direction of the applied magnetic field. These dotted lines that I have shown you, this is due to the induced magnetism. So that induced magnetism is giving the magnetic field lines in the direction of the applied field inside this material. But outside these are the opposite to this one. So this shows that when we are having this paramagnetic material in the magnetic field, it is getting magnetization in the direction of the applied magnetic field. So just by having seen the direction of the magnetic field and the magnetic lines of force, then we can find that this material is given the paramagnetic. In dimagnetic, I show you that the very feeble the lines of force that pass through the material are very less, and that inside the material they oppose the applied magnetic field, and outside that they support the applied magnetic field. So they are getting the magnetism in the direction opposite to the applied magnetic field. This is all about the paramagnetism. So thank you very much.